This is section 2.4, part B, zeros of polynomial functions. The I can statements for this section: I can find real zeros of polynomial functions, and I can find complex zeros of polynomial functions. So when you're finding the list of possible real zeros for a function, it's nice to be able to narrow down your answers. One way to do that is use Descartes' rule of signs. And this tells us if f of x is a polynomial with real coefficients, then the number of positive real zeros is equal to the number of variations in sign of f of x, or less than that by some even number. And the number of negative real zeros is the same as the number of variations in the sign of f of negative x, or less than that by some even number. So if we take a look at this first example, we have g of x. We also need to have g of negative x. So we're going to break this into two parts. To find g of negative x, you just plug in negative x everywhere you have an x value. Now, when you raise a negative value to an odd power, it stays negative. So this is still going to remain negative x. Negative times negative will give us a positive 3x cubed. When you take a negative power and you raise it to an even power, you are going to change it to a positive value. So this is still a plus 2x squared. Negative times negative gives us a plus x, and then we have minus 1. Now we just need to check and see how many times we switch signs. So we go from positive to negative or negative to positive. On g of x, on the positive version, we go from a negative to a positive. We go from a positive to a negative. So we have 2. So positive real zeros there's 2 or 0 of those. Now it's 2 or 0 because it's whatever value you have, or even numbers worth less than that. So if this would have been 3, we would have done 3 or 1. If we subtract another 2 from that, that would give us a negative 1, which isn't possible. So on this, it's 2 or 0. If you just get one sign change, as we do over here, we just go from one positive to a negative. The number of negative real zeros is just 1. There will be one negative real zero. Let's do this again. We have g of x. We also need g of negative x. Negative x to the 4th power makes that a positive. So negative 5 times times a positive x is a negative 5x to the 4th. Negative x to the 3rd power stays negative. So negative x cubed times a positive 4 gives us a negative 4x cubed. Negative x, when I square it, becomes positive. So this will be a plus 7x squared. Negative 2 times negative 2 gives us a plus 2x and plus 1. So let's check and see how many times we change signs. On g of x, we go from a negative to a positive to a negative, and then a negative back to a positive. On g of negative x, we go from a negative to a positive, and then it does not change again. So there are 3 or 1 positive zeros. And there is 1 negative 0. Now we're going to get into some complex zeros. Just as quadratic functions can have real or imaginary zeros, polynomials of higher degree can also have zeros in the complex number system. The fundamental theorem of algebra says a polynomial function of degree n, where n is greater than 0, has at least one 0, whether it's real or imaginary, in the complex number system. We can write it in a linear factorization. If the function of a degree n is greater than 0, then it has n linear factors. So we can do a sub n times x minus c sub 1 times x minus c sub 2, and we're going to have as many factors as we have our degree of our exponent, where a sub n is some non-zero real number, and all your c's are constants, and they're in the complex zeros. The conjugate root theorem says if a polynomial equation in one variable has a root of a form a plus bi, then it also has the complex conjugate of a minus bi would also be a root. This also applies if I have a root. If I know x is equal to 4i, that means x is equal to negative 4i as well. So it doesn't just have to be the plus or minus, it can just be the imaginary number. You will have the positive and negative of that value. So we need to write a polynomial function of least degree with real coefficients in standard form that has negative 2, 4, and 3 minus I as its zeros. To do this, we're first going to write it in the linear factorization form. Remember, when you put something into the parentheses or take it out, you change the sign. So if I have an x that's negative 2, when I put it in the parentheses, it's going to become x plus 2. If I have an x of 4, when I put it in the parentheses, it become a negative 4. We're going to have x minus 3 minus I. And so since we have 3 minus I, we also have to have the conjugate, which is 3 plus I. Now we're just going to FOIL this and distribute, combine like terms as needed to get this in a polynomial form. So let's break these into two different groups. Let's look at this group together and this group together. We're going to factor the pieces in the blue box, and then we'll factor the pieces in the black box, and then we will distribute. So if we FOIL in the blue box first, x times x gives us x squared. X times negative 4 is negative 4x. Inside, 2 times x gives us 2x. And last, 2 times negative 4 gives us negative 8. Inside the black box, we're going to FOIL. X times x gives us x squared. X times negative 3 plus I will be minus x times 3 plus I. Inside, we're going to have minus x times 3 minus I. And last, negative times negatives gives us a positive 3 minus I, 3 plus I. In the blue box, we can combine like terms. Inside the black parentheses, we're going to need to distribute, and we're going to need to FOIL again. If I distribute this negative x here and here, we're going to have negative 3x minus xi. Distribute here and here, we're going to have negative 3x plus xi. And then on this part, we are going to have to FOIL. So if we do first, 3 times 3 gives me 9. Outside, 3 times I is plus 3i. Inside will be minus 3i. And last, negative I squared. We're going to leave that blue set of parentheses alone for right now. But we need to combine like terms on the black set of parentheses. We have x squared. I have a negative 3x and a negative 3x. That gives me negative 6x. I have a minus xi and a plus xi, so those are going to cancel. I have a plus 3i and a minus 3i, So those are going to cancel. And now we have a 9 and a negative I squared. Remember, I squared is equivalent to negative 1. So negative negative 1 turns plus positive. 9 plus 1 will give us 10. So now we have x squared minus 2x minus 8 times x squared minus 6x plus 10. Now we're going to have to distribute these two. So we're going to take the x squared from the blue set of parentheses, and we're going to distribute it here, here, and here. So x squared times x squared gives us x to the 4th. X squared times 6x is negative 6x cubed. X squared times 10 is plus 10x squared. We're then going to take the negative 2x and distribute here, here, and here. So negative 2x times x squared is negative 2x cubed. Negative 2x times 6x is a positive 12x. Negative 2x times 10 is a negative 20x. We are then going to take the negative 8 and distribute here, here, and here. So negative 8 times x squared is negative 8x squared. Negative 8 times a negative 6x is a positive 48x. Negative 8 times 10 gives you a negative 80. Now we just need to combine like terms. There's only one x to the 4th, so we're going to leave that by itself. We have a negative 6x cubed and a negative 2x cubed. Negative 6 and negative 2 gives us a negative 8x cubed. We have a plus 10x squared. We have a minus 8x squared. 10 minus 8 is going to give us a positive 2x squared. We have a 12x and a negative 20x, which is negative 8x. And then we have a positive 48x. So negative 8 plus 48 is going to give us a positive 40x. And then we have this negative 80 by itself at the end. So our function, written in least degree, will be x to the 4th minus 8x cubed plus 2x squared minus 40x minus 80. And this will have the zeros of negative 2, 4, and then the imaginary zeros of 3 minus I and 3 plus I. Notice that there are 3 zeros when you include your 2 imaginary zeros, and there are 4 zeros when you include your 2 imaginary zeros, and this is of degree 4. Factoring polynomial functions over the reals. Every polynomial function of degree n, where n is greater than 0, with real coefficients can be written as the product of linear factors and irreducible quadratic factors, each with real coefficients. So if we take a look at this polynomial function, we first want to write it as the product of linear and irreducible quadratic factors. So we want to find all of the real zeros, break those down into linear factors, and then leave the rest of it as an irreducible quadratic factor. To do this, the first thing we need to do is we need to graph it and find a zero that works. After we graph it, we can see from our graph that we will have a 0 at x is equal to negative 5. So if we take our polynomial and we use synthetic division, we can check negative 5 and make sure it's a 0. If you notice in your polynomial function, we go from x to the 5th to x to the 3rd. So we do need to put a 0 in the placeholder of where x to the 4th should be. Remember, when using synthetic division, you bring the first number straight down. Negative 5 times 1 is negative 5. 0 plus negative 5 is negative 5. Negative 5 times negative 5 gives us a positive 25. When we add down, we will get 7. 5 times 7 is going to give us a negative 35. 30 plus a negative 35 gives us negative 5. Negative 5 times negative 5 is a positive 25. When we add down, we will get 6. Negative 5 times 6 is a negative 30. When we add down, we do get 0. So this is a 0 of our function. If we go back to our graph, it looks like we do have another 0 at x is equal to 2. Remember, you can always use the quotient of your first division on your second one to factor this down farther. We bring our first term straight down, so 2 times 1 is 2. When we add down, negative 5 plus 2 is negative 3. 2 times negative 3 gives us negative 6. 7 minus 6 gives us 1. 2 times 1 is 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. And when we add that down, we do get 0. So we do see that x equals 2 is a 0 of our function. If we go back to our graph, we do see one more 0 on our graph, and that'll be at x equals 3. Again, we're going to use the quotient of our one we factored down the farthest to keep factoring this polynomial down even farther. So 3 times 1 is 3. We add, we get 0. 3 times 0 is 0. We add down, we get 1. 3 times 1 is 3. We add down, we do get 0. Now when we started, this was x to the 5th. We divide once, that gets us x to the 4th. We divide again, that's going to get us x to the 3rd. And if we divide again, this is going to give us x squared. So we had a 0, x equals 5. When you put it in the parentheses, remember you change the sign. Then we had an x of 2, so that's going to be x minus 2. Then we have x minus 3, and we are left with x squared plus 1. Now x squared plus 1 cannot be factored down any farther, because that will give us imaginary numbers, because it will be taking the square root of a negative value, which we cannot do in the real numbers. So this is the product of the linear factors. Sorry, that's for part A. Let me move that up there. So that is your product of linear and irreducible quadratic factors. If we want to just write it as the product of linear factors, we are going to have to factor that last part. Now we need to remember that I squared is equal to negative 1. And if you take the square root of negative 1, that is equal to I. So when we have x squared plus 1 is equal to 0, we can solve that part when we're dealing with imaginary numbers, because we'll get x squared is equal to negative 1. When you take the square root, remember it is plus or minus a value. So x is equal to plus or minus the square root of negative 1, which is I in the imaginary numbers. So we will have zeros at x equals I and x is equal to negative I. So if we rewrite this as the product of all the linear factors, we still have x plus 5, x minus 2, x minus 3, but we will have x plus I and we will have x minus I. So if we list all of the zeros, when we pull them out of the parentheses, remember you change the sign, so we'll have zeros at negative 5, 2, 3, negative I, and I. When you're dealing with complex zeros, you can use synthetic substitution with complex numbers in the same way you use it with real numbers. Doing so can help you factor a polynomial in order to find all of its zeros. So we need to find all of the complex zeros of the polynomial function x to the 4th minus 6x cubed plus 20x squared minus 22x minus 13. We are given that one of our zeros is 2 minus 3i. Now remember, if we have a 0 of 2 minus 3i, we also have a 0 of 2 plus 3i because it is its complex conjugate. So we're going to start using synthetic division. Remember, you bring that first term straight down. 1 times 2 is 2. 1 times negative 3i is negative 3i. When you add straight down, negative 6 plus 2 gives me negative 4, and we're still bringing down that negative 3i. Now we actually have 2 times negative 3i. So we are going to have to multiply 2 minus 3i times negative 4 minus 3i. To do that, we are going to have to FOIL. So 2 times negative 4 gives us negative 8. 2 times negative 3i is going to give us negative 6i. Negative 4 times negative 3i gives us a positive 12i. Negative 3i times negative 3i is a positive 9i squared. But remember, I squared is equal to negative 1. So we combine like terms. I have negative 8. 9 times negative 1 is negative 9. So this gives me negative 17 plus 6i after we combine like terms. So we put this back into our synthetic division. We are still going to add straight down. 20 plus negative 17 is 3 plus 6i. Now we're going to have to do 2 minus 3i times our 3 plus 6i again. So we are going to have to FOIL again. So when we FOIL, we're going to do 2 times 6, which gives us 12. Outside, 2 times 3 is 6i. Inside is going to give us negative 18i. And last will give us a negative 9i squared. Once again, I squared is negative 1. So negative times negative will make this a positive 9. So we combine like terms. 12 plus 9 gives us 21. 6 minus 18 is going to give us a negative 12i. Unfortunately, I had that backwards. It's not 6 plus 3i, it is 3 plus 6i. So let's try foiling that again. 2 times 3 will give us 6. 2 times 6i will give us 12i. Negative 3i times 3 will give us a negative 9i. And negative 3i times 6i will give us a negative 18i squared. But that is negative 1. Negative times negative does turn that positive. So 6 plus 18 is 24 plus 3i. So let's put that back into our synthetic division. Now we add straight down. Negative 22 plus 24 gives us 2 plus 3i. We are going to have to do foiling one more time. We have 2 minus 3i times 2 plus 3i. So 2 times 2 gives us 4. Outside, 2 times 3i is 6i. Inside, negative 3i times 2 is negative 6i. Negative 3 times negative 3, negative 3 times a positive 3 is a negative 9i squared. But I squared is negative 1, so this turns plus positive. So 4 plus 9 gives us 13. Negative 6i and positive 6i is just 0. So if we plug this back into our synthetic, this is negative 13 plus 13, which gives us 0. So that 2 minus 3i is a 0. We have factored it down a little bit. Now remember, if that is a 0, 2 plus 3i will also be a 0. And we can just use our quotient from our first division. We bring 1 straight down. 1 times 2 gives us 2. 3i plus 1 times 1 gives us plus 3i. When we add straight down, those 3i's will cancel, so we're left with negative 2. Negative 2 times 2 gives us negative 4. Negative 2 times 3i gives us a negative 6i. This is going to leave us with negative 1. 2 times negative 1 is negative 2. 3i times negative 1 is negative 3i, and that'll factor down and give us a 0. So we started out with x to the 4th. After one division, we would be left with x to the 3rd. After a second division, we are left with x squared. So far, we have x minus 2 minus 3i, x minus 2 plus 3i, And now we're adding x squared minus 2x minus 1. Now we want to factor this down even farther so we can find all of the real zeros. We cannot factor x squared minus 2x minus 1 and get nice real numbers. These are going to be complex numbers. So we are going to have to use the quadratic formula, or you can use the quad form on your calculator. So our a value in this case is 1, our b value is negative 2, and our c value is negative 1. If you remember your quadratic formula, we know that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. If we plug in these values, we're going to have negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times negative 1 all over 2 times 1. If we simplify that, we have 2 plus or minus the square root of 4 plus 4 all over 2, which is 2 plus or minus the square root of 8 over 2, which we can reduce again. The square root 8 has the factors of 4 and 2. We can take the square root of 4, and we have 2 plus or minus 2 times the square root of 2 all over 2. Now 2 goes into 2, so when we simplify this, 2 divided by 2 gives us 1, plus or minus 2 divided by 2 is 1, radical 2. So those are zeros of our functions. So our 4 zeros will be 2 minus 3i, 2 plus 3i, and plus or minus 1 plus or minus the square root of 2.